My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about the force of a magnetic field on a current carrying a straight wire. What factors that decide the size of the force and what factors that decide the direction of the force. Also, we'll be able to learn about Tesla's definition of magnetic flux density, and we'll solve some problems. So let's get started. Magnetic effect of the electric current. Force of a magnetic field on a current carrying a straight wire. We call this motor effect. Force of a magnetic field on a current carrying a straight wire. It is an experiment, experiment in which the energy is converted from electrical energy into mechanical energy. In front of you on the screen, a straight wire is placed perpendicularly to a magnetic field. A current is then sent into the wire, and the wire moves as it is acted upon by a magnetic force. The direction of the force, direction of motion, depends on the direction of the current. That's to say, if the direction of the current is reversed, the direction of motion is also reversed. And now, talking about Fleming's left-hand rule. What about Fleming's left-hand rule? Yes, Fleming's left-hand rule is used for the determination of the direction of force when a current causes motion. The thumb indicates motion, forefinger indicates field, and second indicates direction of the current. So, once again, talking about Fleming's left-hand rule. What about the statement of the rule? First of all, it is used for determining, as I said, the direction of motion when a current causes motion. We start with a current is sent into the wire, then the wire is acted upon by a force and moves. So it is used when a current causes motion. Fleming's left-hand rule states, first of all, place the forefinger, second finger, and the thumb of the left hand mutually perpendicular to each other. Mutually at right angles to each other. Then, if the forefinger points in the direction of the field, forefinger points in the direction of the field. Field direction is from the north to the south. Then, if the forefinger points in the direction of the field and the second finger in the direction of the current, conventional current, your attention, direction of the conventional current, the current that moves from the positive, plate into the negative. The thumb will point in the direction of motion. Once again, thumb indicates the force or the thrust. And what about the forefinger? It indicates the direction of the field. And second indicates the direction of the current. This was about Fleming's left-hand rule, the rule used to determine the direction of motion of a current carrying a straight wire placed in a magnetic field, placed at right angle to a magnetic field. And now we've got a give reason. We want to explain why the wire moves, why it is acted upon by a force. So let's try to answer the following give reason. When a current carrying a straight wire is placed at right angles to a magnetic field, the wire moves. Let me say it again. When a current carrying a straight wire is placed at right angles to a magnetic field, the wire moves. Okay, in front of you we've got, of course, two fields. Two fields, yes. One of them is due to the current flowing in the wire, due to the flow of the charges, electrons in the wire. Flow of electrons creates magnetic field, and the field of the magnet, they superpose, okay? And what happens? Okay, in front of you it is shown. On one side of the wire, the two fields have the same direction, so the density of the field increases. On the opposite side, they flow in opposite directions, so the density decreases. Since flux lines repel each other sideways, the wire is acted upon by a force and then moves. Okay, the wire moves due to, once again, the wire moves due to the interaction between the two fields. Okay. The magnetic field of the current carrying wire and the uniform field of the magnet. Two fields. Field due to the current and field due to the magnet. When the two fields combine, interact, the magnetic flux lines get closer on one side of the wire. It means density increases. Magnetic flux lines get closer on one side of the wire, where the lines of force, lines of the magnetic flux, lines of the two fields are in the same direction. Density increases. Now we've got a region of high magnetic intensity. Okay, a region of high magnetic intensity is produced. The flux lines are set apart on the opposite side, okay, of the wire, where the lines of the two fields are in opposite directions. Now we've got a region of low magnetic intensity or magnetic flux density. The wire moves away from the region of higher intensity to the region of lower intensity. In this way, we managed to explain why, when a current carrying a straight wire is placed at right angles to a field, a magnetic field, the wire is acted upon by a force and moves. Now talking about the factors that determine the magnitude of the force, size of the force. So once again, factors affecting the force of a magnetic field on a current carrying a straight wire. The force is directly proportional to, first factor is the current intensity, the intensity of the current flowing through the wire, when the rest of factors, of course, are kept unchanged. So first factor is the current intensity. Okay, second factor is the length of the wire. Length of the wire is denoted by, yes, letter L, capital L, when the rest of factors are unchanged. Also, the third factor is the strength of the field, magnetic flux density, denoted by beta. Okay, and of course, we keep other factors are unchanged. And the last factor is the sine of the angle that the wire makes with the field, sine theta, angle between the field and the wire. Okay. Now we'll combine all factors in just one expression. So the force is proportional to BIL sine theta. Let me say it again. B stands for magnetic flux density. I stands for current intensity passing through the wire. L is the length of the wire placed in the field. Theta is the angle between the wire and the magnetic field. Proportionality sign is replaced by equality sign as usual. Then we put a constant. The constant is denoted by letter K. But there is something very important about this constant. K equals 1 when the unit of magnetic flux density is Tesla. Okay, so K equals 1 when the unit of the magnetic flux density is Tesla. Okay, so we can say now the force of a magnetic field on a wire carrying current is equal to BIL sine theta. So the force equals BIL sine theta. In this way, we can say magnetic flux density equals F over IL sine theta. Okay, why I'm doing so? Just a minute and you'll be able to know. Okay, now talking about magnetic flux density. We want to define magnetic flux density. Magnetic flux density beta equals F over IL sine theta. So it will be the magnetic flux density of a uniform magnetic field at a point is numerically equal to the force that acts on 1 meter in length carrying a current of 1 ampere and placed at right angles to the field at that point. And now we want to define the unit of magnetic flux density. We want to define Tesla. What's meant by Tesla? Since magnetic flux density equals F over IL sine theta, so we can say Tesla equals Newton over ampere times meter. So Tesla is the magnetic flux density. It is the magnetic flux density of the uniform magnetic field, which exerts a force of 1 Newton on a wire 1 meter in length, carrying a current of 1 ampere and placed at right angles to the field. And now we've got a question. What's meant by the magnetic flux density of a uniform magnetic field at a point is equal to 0.02 Tesla? What's meant by magnetic flux density of uniform field at a point is equal to 0.02 Tesla? Okay, thank you very much. It means that a force of 0.02 Newton will act on a wire. What about the wire? Dimensions of the wire, it is 1 meter in length, carrying a current of 1 ampere when placed at right angles to the field at that mentioned point. Note, we've got something very important here. When the wire makes an angle theta with the field, the formula, the relation used to determine the magnitude of the force is F is equal to BIL sine theta. Thus, okay, when the field makes an angle theta with the wire. Okay, resolution here, and the formula used is F is equal to BIL sine theta. BIL sine theta. Okay. When the wire is placed parallel to the field, okay, the wire will not experience any force, simply because F will be equal to 0 when theta equals 0. The formula F equals BIL sine theta. Sine 0 equals 0. Okay, the field is now parallel to the wire. What about the force? The force will be equal to 0. Okay, and what about when the wire is at right angles to the field? If the field makes an angle 90, the wire experiences the greatest force. Okay, wire makes an angle, yes, 90 with the field. Then the force is just BIL, as sine 90 equals 1. Now we've got a question. Explain. Carrying current is placed in a magnetic field, but it doesn't experience any force. No force acts on it. Can you explain why? Simply because the wire must be placed parallel to the field. Theta equals 0, so the force is equal to 0 as F is equal to BIL sine theta, sine 0 equals 0. Okay. And now talking about force between current carrying conductors, two straight wires, and Fleming's left-hand rule. Okay, we'll start with the force of the magnetic field of wire B, field produced due to the flow of the current in wire B on a length L of wire A. So the force acts on wire A and it is produced from wire B. Your attention, please. So in front of you we've got two wires. Wire A, which carries the current, yes, intensity denoted by I1, and I2 is the current that flows in wire B. Okay. Now we want to determine the force, the magnetic force produced by wire B on a length L of wire A. So the force FB equals, yes, magnetic flux density of wire B. I1 is the current flowing through, yes, wire A. L is the length of wire A. Okay, so we can say the force produced by the magnetic field of wire B is equal to, yes, 2 times 10 to the power of negative 7 I2 over D times I1 times L. Okay, so the force equals 2 times 10 power negative 7 I1 I2, yes, L over D. This is equation number 1. Okay, and now we want to calculate the force of the magnetic field of wire A on a length L of wire B. Okay, once again, the force produced by magnetic field of wire A equals BA I2 L. Okay, substituting for BA, yes, it is 2 times 10 to the power of negative 7 I1 over D times I2 L. So the force is equal to 2 times 10 to the power of negative 7 I1 I2 L over D. This is the equation number 2. Okay, from 1 and 2 we can conclude something. Yes, the two forces are equal. Okay, so it means each meter length of the two wires experiences the same force. It means the force on the same length of each of the two wires is the same. The force is equal to, yes, 2 times 10 power negative 7 I1 I2 L over D. D is the distance between the two wires. In general, the force is determined from the expression mu, which is the permeability I1 I2 L over 2 pi D. Mu, as I said, is the permeability of the medium. And now we've got questions, answered questions, and we'll try to answer them together. First of all, mention one use of each of the following. We want just one use of each of the following. Maxwell's corkscrew rule. We call it the right-hand corkscrew rule. One use for it. Okay. It determines the direction of the magnetic field produced by a current carrying a straight wire. So it determines the direction of the magnetic field produced by a current carrying a straight wire. It states, imagine a cork screw being screwed along the wire in the direction of the current. The direction of rotation of the screw gives the direction of the magnetic field. So it determines the direction of the magnetic field due to a current flowing in a straight wire. Also, it can be used to determine the direction of the magnetic field at the center of a current carrying, circular coil. Also, we want one use for Ampere's right-hand rule. One use for Ampere's right-hand rule. It determines, Ampere's right hand determines the direction of the magnetic field due to a current carrying a straight wire. One use for Fleming's left-hand rule. Yes, it determines the direction of the magnetic force, direction of the motion, direction of the magnetic force exerted by a magnetic field on a current carrying a straight wire placed perpendicular to the field. Second type of question, give reason for. The straight current carrying wire shown in the following figure experiences no force. We've got a straight wire that carries a current and placed inside a solenoid, but no force acts on it, though there is current in the solenoid. Okay, we've got a wire, that carries a current placed, inside a solenoid carrying current, but no force acts on the wire. Why? Although it is placed inside a current carrying solenoid. The field of the solenoid is parallel to the wire, so it doesn't exert any magnetic force on it. So the answer is the field of the solenoid is parallel to the wire, so it doesn't exert any magnetic force on it. Since the force is determined from the expression BIL sine theta, so force is equal to 0 when, theta is equal to, when theta is equal to 0 as sine 0 is 0. And now talking about another important topic, which is torque acting on a rectangular coil carrying current placed in a magnetic field. In front of you, we've got a coil that carries current and placed in a magnetic field, uniform magnetic field. In the horizontal position, let's describe the horizontal position. It is the position where the plane of the coil is parallel to the field. The magnetic force, the magnetic flux lines are parallel to both sides, BC and AD, so they experience no force. But sides AB and DC are perpendicular to the field lines, so they are acted upon by two forces equal in magnitude, opposite in direction, and they are parallel. So they'll form a couple. They are acted upon by two forces equal in magnitude and opposite in direction. These two forces are parallel, so they produce a couple, which causes the coil to rotate around its axis. So the magnitude of the torque is determined or is obtained from one of the two forces times the normal distance between the two forces. So torque equals BIL, one of the forces, times the normal distance. Normal distance is LBC. So torque equals BI between two brackets LAB times LBC, which is the face area of the coil. So we can say the torque equals BIA. As I said, LAB times LBC equals the cross-sectional area of the coil. If the coil consists of n number of turns, the total torque is determined from the expression BIAN. Also, we can say the torque is equal to BMD. What is MD? It is the magnetic dipole moment of the coil. And of course, it is equal to just IAN. I, current intensity flowing through the coil. A is the area of the coil, face area, N is the number of turns on the coil. And now, let's define magnetic dipole moment. It is the torque exerted on a coil when placed with its plane parallel to a magnetic field of density 1 Tesla. In this case, the torque is equal to the magnetic dipole when the magnetic flux density is equal to 1 Tesla. Unit of the magnetic dipole moment is ampere times meter. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.